What if every decision you've ever made actually happened? Not in some metaphorical sense, but physically, tangibly, in universes as real as the one you're experiencing right now. What if the act of simply observing something doesn't reveal what was already there, but instead splits reality itself into countless parallel streams of existence, each one continuing forward with its own version of you inside it? This isn't science fiction. It's a serious interpretation of quantum mechanics that has been debated, refined, and tested by physicists for nearly 70 years. The implications are staggering. If this view is correct, then every moment you exist, reality multiplies. Every quantum interaction in your brain, every photon striking your retina, every electron firing in your neurons creates new branches of the universe. Right now, as you read these words, you are splitting into versions that are having slightly different experiences, thinking marginally different thoughts, existing in parallel worlds that will never communicate with each other again. The theory sounds impossible. It seems to violate everything we know about how reality works. Yet, it emerges naturally from the mathematics of quantum mechanics when you follow the equations honestly to their conclusion, without adding arbitrary rules or special exceptions. No extra assumptions, no mysterious collapses. Just the straightforward application of the most successful theory in the history of physics. And increasingly, scientists are finding that this interpretation not only makes sense of quantum weirdness, but predicts phenomena we can actually test. We may be closer than ever to proving that parallel universes aren't just possible, they're inevitable. The story begins in 1957. In a graduate student's office at Princeton University, Hugh Everett had been working on a problem that had troubled physicists since quantum mechanics was first formulated in the 1920 seconds. According to the standard view taught in every textbook, quantum particles exist in multiple states simultaneously until someone observes them. At that moment, the particle mysteriously collapses into one definite state. An electron that was spinning both up and down suddenly becomes just spin up or spin down. A particle that was in many places at once instantly localizes to a single position. But this collapse was never part of the actual mathematics. The Schrödinger equation, which governs how quantum systems evolve, describes smooth, continuous change. Nothing in the equation says anything about sudden collapse or special roles for observers. The collapse was added by hand, an extra rule grafted onto the theory to make it match what experimenters saw. Yet nobody could explain when collapse happened, or how, or what counted as an observation. Was consciousness required? Did measuring devices have some special status that ordinary matter lacked? The questions multiplied without satisfying answers. Everett approached his thesis advisor, John Wheeler, with a radical solution. What if particles never collapse at all? What if the mathematics are telling us exactly what happens, and we've simply been too timid to accept it? The equation says that all possible outcomes of a measurement occur. Not that they might occur, or that one becomes real while others vanish. All of them happen, each in its own branch of physical reality. Wheeler was disturbed by the implications. If Everett was right, then every quantum measurement literally splits the universe. Not metaphorically, not in some abstract mathematical space. Actual, physical realities diverge from each other like roads forking in endless directions. Wheeler worried about his student's reputation. He urged Everett to soften the language, to present it as just one possible interpretation, rather than a claim about what truly exists. Everett refused. The mathematics were clear. Denying the conclusion meant denying the equations themselves. Here's what Everett's math revealed. When you measure an electron's position, you don't force it to choose where it is. Instead, you become entangled with it. Your quantum state becomes correlated with the electron's quantum state. One version of you sees the electron here. Another version, equally real, equally conscious, sees it there. Both versions continue existing. Both have continuous streams of experience. Both are convinced they're the only version because they cannot perceive the other branch. The universe has split, but from inside any single branch, it feels like collapse occurred. This wasn't philosophy or interpretation in the sense of adding something to the theory. This was what happened when you applied quantum mechanics to everything, including the measuring device and the person doing the measuring. No special rules, no privileged role for observers, just quantum mechanics, taken seriously and applied consistently to the entire universe. For decades, most physicists ignored Everett's work. It seemed too strange, too extravagant. Why should we believe in countless invisible parallel universes when we could just say the wave function collapses and be done with it? The fact that nobody could explain how collapse happened seemed like a minor detail compared to accepting that reality splits every microsecond into astronomical numbers of parallel worlds. But the problems with collapse theories grew more acute as experiments became more sophisticated. Quantum entanglement was verified repeatedly in laboratories worldwide. When two particles interact and become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein had called this spooky action at a distance and believed it proved quantum mechanics was incomplete. He was wrong. The entanglement is real. Particles that have interacted remain connected in ways that transcend space and time as we normally understand them. The thing is, entanglement makes perfect sense in Everett's interpretation. When two particles interact, the combined wave function describes both particles together. Measuring one particle splits the observer into branches correlated with different outcomes. From each branch, it appears that measuring particle A instantly revealed information about distant particle B. But both particles existed in superposition all along. The apparent instant connection is an artifact of which branch you ended up in after becoming entangled with the system. Other interpretations struggled to explain entanglement without violating relativity, or adding invisible guiding waves or invoking consciousness. Everett's interpretation required none of these additions. It simply said, the wave function describes reality. When particles interact, they become part of one combined system. When you measure that system, you join it. The universe doesn't collapse. You diverge into versions experiencing different outcomes. In the 1,970 seconds, physicist David Deutsch at Oxford recognized something profound about Everett's many worlds. If parallel realities exist, they should have measurable consequences. Deutsch was working on the theoretical foundations of quantum computation. He realized that quantum computers, if they could be built, would be impossibly powerful. A quantum computer with just 300 quantum bits could process information equivalent to more particles than exist in the entire observable universe. Where would that computational power come from? Deutsch argued it could only come from parallel universes. When a quantum computer runs a calculation, it places its quantum bits into superposition. Each quantum bit can be 0 and 1 simultaneously. 300 quantum bits represent 2 to the power of 300 different states at once. In Everett's interpretation, each state exists in a different branch of reality. The quantum computer is literally performing calculations in parallel across countless parallel worlds. The computation happens simultaneously in all these branches. Then, through quantum interference, the results are brought together to give you an answer in this branch. This wasn't just philosophical speculation. Deutsch showed that quantum computers should be able to solve certain problems exponentially faster than any classical computer. They could factor large numbers, search unsorted databases, and simulate quantum systems with ease. If parallel worlds didn't exist, where was all this computational power coming from? How could 300 quantum bits access more processing capability than all the matter in the universe unless they were reaching across realities? The argument convinced many physicists to take Everett seriously. Quantum computers were no longer pure theory. Research groups worldwide began building primitive versions. The devices worked, not perfectly, and not at large scales yet, but they demonstrated quantum speedup in small problems. They showed that quantum superposition could be harnessed for computation. According to Deutsch, every time these machines run, they prove parallel universes exist. They're borrowing computational resources from other branches of reality. Meanwhile, experiments continued to confirm the predictions of quantum mechanics in ever more dramatic ways. Particles really do exist in multiple states simultaneously before measurement. They really do interfere with themselves. They really do become entangled across vast distances. All the weird phenomena that early quantum pioneers found disturbing turned out to be absolutely, undeniably real. The only question was how to interpret what this reality means. The Copenhagen interpretation, which had dominated for decades, began to look less satisfying. It said quantum mechanics only describes our knowledge, not reality itself. When we measure something, our knowledge updates, and the wave function collapses to reflect this new information. But this seemed like philosophical retreat. Quantum mechanics is supposed to be a fundamental theory of nature. If it only describes knowledge rather than reality, what describes actual physical processes? Other interpretations tried different approaches. Pilot wave theory, developed by Louis de Broglie and later refined by David Bohm, proposed that particles have definite positions at all times, guided by a hidden wave field. This saved the intuition that things are definitely somewhere, even when we're not looking. But it required adding elements to the theory that could never be observed directly. It also made the theory non-local in disturbing ways. Change something here, and hidden influences must propagate everywhere instantly, faster than light. Everett's interpretation avoided these problems by taking the simplest possible stance. The wave function is real. It describes everything that exists. Nothing is hidden. Nothing collapses. The appearance of collapse is just what branching looks like from inside a branch. You don't see other branches because you became entangled with the measured system and diverged from versions of yourself that saw different outcomes. But if reality splits every time a quantum measurement occurs, and quantum events happen constantly at every scale, then how many parallel worlds exist? The mathematics of quantum mechanics doesn't specify a number. Some physicists argue the total must be infinite, because quantum variables like position are continuous. An electron can be at any point in space, not just a discrete location. Each possible position represents a different branch. With infinite possible positions and infinite particles, the number of branches becomes infinite in ways that exceed ordinary infinity. Others suggest the number might be enormous, but finite. If space and time are fundamentally discrete at the tiniest scales, the Planck scale, then the number of possible quantum states is large but countable. Even so, the number would dwarf anything we encounter in ordinary experience. David Deutsch put it bluntly, "The number of parallel worlds is not 5, not 1,000,000, but vastly, incomprehensibly larger than human intuition can grasp. Every moment, reality multiplies. Not someday, not in special situations, but constantly, everywhere, at every scale where quantum mechanics applies. Which is to say, everywhere. Quantum mechanics governs atoms, molecules, biological systems, everything made of matter and energy. There's no threshold where quantum mechanics stops and something else begins. There's just physics, describing a universe that branches perpetually into parallel streams of existence. In your brain right now, electrons are transitioning between energy states as neurons fire. Each transition involves quantum uncertainty. Each uncertainty splits reality. Most of these splits rejoin almost immediately because macroscopic systems like brains interact strongly with their environment, causing rapid decoherence. The branches can't interfere with each other once decoherence occurs, so they become effectively separate worlds. But the branching still happens, trillions of times per second, just in your nervous system alone. Scale this across the observable universe. Every star emits quadrillions of photons every second. Each photon that interacts with an atom creates entanglement and spawns branches. Cosmic rays bombard planetary atmospheres. Radioactive decay occurs in rocks. Neutrinos occasionally interact with matter. The branching rate becomes incomprehensible. Sean Carroll, a physicist who has worked extensively on interpreting quantum mechanics, estimates that the rate of branching in our local vicinity alone exceeds billions upon billions of events per second. The total across the cosmos is unimaginably higher. Does this mean your choices don't matter? If every possible decision occurs in some branch, does it make any difference which branch you experience? This is one of the most common objections to the many worlds interpretation. It seems to render choice meaningless. But this misunderstands what choice means in this framework. You can't control whether other branches exist, but you absolutely control which branch contains you going forward. When you make a decision, you determine your future experience. The version of you in this branch faces the consequences of your choices here. Other versions made different choices and faced different consequences. Both are real. Both matter to the version experiencing them. Think of it this way. In a classical, single timeline universe, your choices might still be determined by prior causes stretching back to the Big Bang. Determinism has always been a challenge for free will, regardless of quantum mechanics. The many-worlds interpretation doesn't make this problem worse. It reframes it. Your choices are determined in the sense that the universal wave function evolves according to fixed laws. But those choices determine which branch you experience, which is the only thing that matters for your subjective sense of agency and moral responsibility. Some philosophers argue this preserves everything important about free will. Others remain troubled. The debate continues. What's clear is that the many-worlds interpretation doesn't dissolve the question so much as relocate it. Free will, moral responsibility, personal identity, all these concepts must be understood in terms of branching rather than collapse. Whether that's satisfying depends on what you think these concepts require. What Everett discovered goes far beyond quantum mechanics. If his interpretation is correct, then the universe is vastly larger and stranger than it appears. The world you see around you is one thread in an infinite tapestry of parallel realities. Every version of history that could have happened has happened somewhere in the quantum multiverse. Your life contains countless variations, all unfolding simultaneously in isolated branches. Each one as real as the existence you're experiencing right now, and we may be on the verge of proving it. Not through philosophy or mathematics alone, but through actual experiments that could demonstrate parallel universes exist. The evidence could be written across the sky in ancient light from the dawn of time. It could be encoded in the computational power of quantum machines. It could be hidden in subtle interference effects between worlds that haven't quite separated yet. Scientists are designing tests right now that could answer the question definitively within our lifetimes. But before we explore that evidence, we need to understand exactly how the universe branches, what determines the structure of these parallel worlds, and why we experience reality the way we do if everything exists in superposition. We need to look at the fundamental nature of quantum mechanics itself, at the mathematics that forced Everett to his radical conclusion. Because the case for parallel universes isn't built on speculation. It's built on taking the most successful scientific theory ever formulated and following it honestly wherever it leads. To understand why reality might split, we need to examine what happens at the smallest scales of existence. Quantum mechanics reveals that the microscopic world behaves nothing like the familiar realm of everyday objects. At the quantum level, particles don't have definite properties until something forces a measurement. An electron doesn't occupy a specific position or move with a particular speed. Instead, it exists as a wave of probability spread across space, describing all possible positions and velocities simultaneously. This isn't ignorance on our part. It's not that the electron has a definite position we simply don't know yet. The electron genuinely exists in multiple states at once, a condition physicists call superposition. The wave function, the mathematical object describing the electron's quantum state, encompasses all these possibilities. Only when we measure the electron does it appear to occupy one definite location. Before measurement, the electron is everywhere it could possibly be, all at once. The classic demonstration of this strangeness is the double-slit experiment, first performed in the early 19th century with light, then later reproduced with electrons and even large molecules. Take a barrier with two narrow slits cut into it, fire individual electrons at this barrier, one at a time, and record where each electron strikes a detection screen on the far side. If electrons behave like tiny classical particles, each one would pass through either the left slit or the right slit, then travel in a straight line to hit the screen. After many electrons, you'd see two bright bands on the screen, one behind each slit. That's not what happens. Instead, an interference pattern emerges. Alternating bands of light and dark spread across the screen. The signature of wave interference, bright bands appear where wave peaks from both paths align and reinforce each other. Dark bands form where peaks from one path cancel troughs from the other. This is exactly what you'd see if you sent water waves through two openings. The waves spread out, overlap, and create an interference pattern. But here's the truly bizarre part. We're sending electrons through one at a time. Each electron creates a single dot on the detection screen. There's nothing to interfere with. Yet after many electrons pass through, the interference pattern appears. The only explanation is that each individual electron somehow passes through both slits simultaneously. The electron exists in superposition, taking both paths at once. The electron interferes with itself, and this interference determines where it's likely to strike the screen. Now add one more element to the experiment. Place detectors at each slit to measure which path each electron actually takes. Suddenly, the interference pattern vanishes. The electrons now behave like classical particles, passing through one slit or the other, but never both. The mere act of measuring which path the electron took destroys the superposition and eliminates the interference. This is the measurement problem in its starkest form. Observation fundamentally changes what happens. Traditional interpretations claim that measurement causes the wave function to collapse. The electron was in superposition, spread across both paths, existing in multiple states simultaneously. Then we looked, and the wave function collapsed to a single definite state. The electron retroactively became the kind of thing that only went through one slit. But this explanation raises profound questions. What constitutes a measurement? Does it require a conscious observer? Exactly when does collapse occur? The equations of quantum mechanics say nothing about collapse. It's not in the mathematics. It's an additional assumption, added to reconcile theory with what we observe. Everett's interpretation offers a completely different picture. The electron never collapses. Neither do you. Before you measured which slit the electron used, you existed in superposition too. Your brain state was entangled with the electron's quantum state. After the measurement, one version of you detected the electron at the left slit, another version detected it at the right slit. Both versions are real. Both are conscious. Both continue experiencing their respective realities. From inside each branch, you see the electron going through only one slit because you became entangled with it in that particular way. This applies to everything, not just electrons in artificial laboratory setups. Photons entering your eye right now interact with molecules in your retina. Those molecules change shape, triggering chemical cascades that send electrical signals through your optic nerve. Each step involves quantum interactions. Each interaction creates entanglement. Each entanglement splits the universal wave function. You're constantly branching into versions, experiencing slightly different patterns of light, slightly different neural activations, slightly different thoughts. The universe exists in superposition at every level, from the smallest particles to the largest structures. All possible arrangements of matter and energy coexist in the universal wave function. We perceive only one arrangement because we're part of the system. We can't step outside to see the full superposition. We ride one branch through quantum configuration space, while countless other branches diverge around us, each containing versions of us experiencing different outcomes. If this seems impossible to accept, consider that quantum superposition has been directly measured for increasingly large systems, not just individual particles, but atoms, small molecules, and even carefully prepared collections of billions of atoms. Experiments have demonstrated that these systems genuinely exist in multiple states simultaneously before measurement forces them into definite configurations. The mathematics works perfectly. The predictions are confirmed. What remains controversial is whether this principle scales up to include human observers and entire universes. The key to understanding how branching works lies in the concept of quantum entanglement. When two particles interact, their wave functions merge into a single combined description. Before the interaction, you could describe each particle independently. Particle A had its own properties. Particle B had its own properties. Simple, separate. After they interact, this separation becomes impossible. A single, entangled state now describes both particles together as one unified quantum system. This entanglement persists even if you move the particles to opposite ends of the galaxy. Measure a property of particle A, and you instantly gain knowledge about particle B. The correlation appears faster than light could travel between them. Einstein found this so disturbing that he proposed it proved quantum mechanics must be incomplete. Perhaps hidden variables existed, carrying information between the particles through normal means, and quantum mechanics simply failed to account for these variables. John Bell proved in 1964 that Einstein was wrong. Bell derived mathematical inequalities that any hidden variable theory must satisfy. Experiments systematically violate those inequalities. The correlations between entangled particles are stronger than any classical mechanism could produce. The particles really do share information instantaneously, not because signals pass between them, but because they're not truly separate entities. They're two parts of one quantum system, described by one wave function. In the many worlds, interpretation, entanglement is the mechanism that creates branches. When particles in your brain interact with each other, they become entangled. The universal wave function splits. One branch contains neurons in state A. Another branch contains neurons in state B. You split into versions experiencing different neural configurations, different thoughts, different perceptions. This branching happens constantly at every level of physical reality. Consider the rate of quantum interactions around you. Air molecules collide with each other roughly 1 billion times per second in the room where you're sitting. Each collision entangles the molecules. Each entanglement splits reality. Photons from your screen strike your retina at a rate of trillions per second. Each photon creates entanglement and spawns branches where you saw slightly different patterns. The number of branches grows exponentially. Start with one universe. A single entanglement creates 2 branches. Another entanglement creates 4. After just 100 entanglements, you have more branches than atoms in the visible universe. How many branches exist right now, at this very moment? Nobody knows with certainty. The mathematics of quantum mechanics doesn't specify whether the total number is finite or infinite. Some physicists argue the number must be infinite because the universe contains continuous variables like position and momentum. If an electron can be at any point in space, not just discrete locations, then there are infinite possible positions, and therefore infinite branches corresponding to different positions. Others suggest the number might be enormous, but finite if space and time are fundamentally discrete at the Planck scale, the smallest meaningful length in physics, about 10 to the negative 35 meters. At that scale, space itself might be quantized into discrete units, like pixels in an image. If so, the number of possible quantum states becomes vast but countable. Even then, the number would exceed anything expressible in ordinary notation. After 1,000 entanglements, you'd have more branches than can be meaningfully described with familiar mathematical tools. Each branch is fully real. Each contains observers like you. Each evolves according to the same physical laws. The branches cannot communicate with each other directly. Once splitting occurs, the branches decohere and become causally isolated. Information cannot pass between them through any normal means. Decoherence happens when a quantum system interacts with its environment. These interactions destroy the delicate quantum relationships that allow different parts of a superposition to interfere with each other. Your brain is made of roughly 86 billion neurons. Each neuron contains trillions of atoms. These atoms interact constantly with each other and with the surrounding environment molecules in cerebrospinal fluid, thermal fluctuations, electromagnetic fields. The interactions create entanglement so rapidly that different versions of you become isolated from each other in microseconds. Once decoherence occurs, the branches cannot interfere. They evolve independently. You, in this branch, have no way to access memories or experiences from other branches. They exist, but you cannot perceive them because quantum interference has been suppressed. This explains why the macroscopic world appears classical, even though quantum mechanics governs everything. Large objects made of many particles interact so strongly with their environment that decoherence happens almost instantaneously. Superposition survives only as long as the system remains isolated. For a single electron in carefully controlled laboratory conditions, isolation can be maintained for seconds or even minutes. For a cat, a person, or a planet, decoherence occurs faster than you can blink. The quantum world becomes the classical world through environmental interaction, not through any fundamental transition or collapse. Yet the branching still happens. Even though quantum effects wash out quickly at large scales, the splitting of the wave function continues. Every quantum event in every atom creates new branches. Most of these branches remain nearly identical to each other. The differences are minute, statistically insignificant. Versions of you where one specific electron in one specific atom was in a slightly different energy state. These branches quickly converge back to similar macroscopic configurations because classical physics dominates at observable scales. But occasionally, quantum events occur at critical moments. A neuron sits precisely at its firing threshold. Whether it fires depends on quantum fluctuations in the channels that allow ions to pass through its membrane. Quantum mechanics says those channels exist in superposition. The universal wave function branches. In one branch, the neuron fires, and you think thought X. In another branch, the neuron remains silent, and you think thought Y. Both versions continue existing in separate realities. Scale this across billions of neurons processing information continuously. The number of branches where your thoughts differ from this moment grows rapidly. In most branches, you're thinking nearly identical thoughts because most quantum events don't significantly affect macroscopic neural activity. But in some branches, a critical fluctuation caused a different cascade of neural firing. You're thinking about something else. Your attention shifted. You made a different decision. Extend this pattern across your entire lifetime. Every moment contains billions of quantum events in your nervous system. Most produce branches that reconverge quickly because classical physics constrains the large-scale behavior. But occasionally, quantum events occur at decision points. You hesitated before speaking. You reconsidered a choice. A memory surfaced or stayed buried. These moments generate branches that diverge substantially over time. The divergence compounds. Versions of you made different friends, pursued different careers, live in different cities. All these versions experience themselves as the only version. Each has continuous memories stretching back to childhood. Each feels like the real you because From inside their branch, they are. The others are invisible. From inside any particular branch, the rest of the multiverse is completely inaccessible. This doesn't mean you lack continuity of identity. The you reading these words right now is a real person with real experiences. Your subjective sense of self is not an illusion, it's just incomplete. You're one thread in a vast tapestry of related selves, all experiencing their own versions of reality, all convinced they're the only one. The question of personal identity becomes complex in this framework. Are all these versions really you? They share your past up to the point of branching. They have your memories, your personality traits, your goals and fears. Yet they diverge. Over time, they become different people with different experiences and different characteristics. Which one is the real you? The answer seems to be all of them, or none of them. The concept of a single, unique you breaks down when reality branches. What remains is a network of related conscious experiences, each one feeling like a continuous self from the inside. This has profound implications for how we think about death. In the many worlds interpretation, there are branches where you survive accidents that killed you in this branch. Quantum events occur differently at critical moments. A neuron fired in a slightly different pattern. Your reflexes were microseconds faster. You made a different choice that avoided danger. Those versions of you continue living, unaware that in countless other branches, their existence ended. Does this mean you're immortal in some sense? From your subjective perspective, you only experience the branches where you survive. Every time you face potential death, quantum branching ensures some versions of you continue. You can never experience your own death because dead versions stop having experiences. Only living versions remain conscious and aware. This is sometimes called quantum immortality, though most physicists who accept the many worlds interpretation find the concept troubling and potentially meaningless. The problem is that the vast majority of branches lead to death eventually. You might survive in some branches, but the measure of those branches, their quantum probability weight, becomes vanishingly small as you age. Saying you're subjectively immortal because some version always survives is like saying you're immortal because you can imagine not dying. The versions that survive become increasingly unlikely, existing in tinier and tinier corners of the quantum multiverse. What matters for your experience reality is the typical branch, not the extreme outliers. And in typical branches, physics works the way it appears to work. People age, they die. The fact that some vanishingly improbable branch exists where you survive against all odds doesn't change the practical reality that you should expect to experience what happens in high probability branches. Quantum immortality might be technically true in some sense, but it doesn't offer much comfort. The deeper question is what it means for something to be you when countless versions exist simultaneously. Perhaps personal identity is not the discrete, singular thing we intuitively imagine. Perhaps it's more like a river that branches into distributaries. Each stream carries some of the original water, flows through its own landscape, eventually reaches the sea. None is more real than the others. All are equally the river, yet all are distinct. Or perhaps identity is better understood as a narrative, a story you tell yourself about continuity across time. In the many worlds interpretation, that story branches. Multiple narratives continue from each moment, each one coherent from its own perspective, each one legitimately claiming connection to the past you remember. The you that exists is not a thing but a process, a pattern of information and experience unfolding through time and across branches of reality. These philosophical implications trouble many people. The many worlds interpretation seems to multiply mysteries rather than solve them. If accepting quantum mechanics means accepting that you split into countless versions every moment, perhaps we should look for alternative interpretations that preserve a single, definite reality. Perhaps the price of taking the mathematics literally is too high, yet the alternatives come with their own costs. The Copenhagen interpretation requires consciousness or measurement to play a special role in physics, which seems to place human observers at the center of physical law in an uncomfortable way. Pilot wave theory adds hidden variables that can never be observed and makes the theory non-local in ways that conflict with relativity. Objective collapse theories, like the one proposed by Roger Penrose, require modifying the Schrödinger equation and adding new physics beyond standard quantum mechanics. The many worlds interpretation requires no such additions. It simply says, the Schrödinger equation is correct. Apply it to everything, including measuring devices and observers. Don't add collapse by hand. Don't invent hidden variables. Don't make consciousness special. Just let the mathematics tell you what reality is. When you do that, branching emerges naturally. Parallel universes are not an assumption, they're a consequence of taking quantum mechanics seriously. Whether you find this convincing depends partly on your philosophical intuitions about what counts as a good scientific theory. Should we prefer theories that match our everyday intuitions about reality, even if they require adding unexplained elements? Or should we follow the mathematics wherever it leads, even if the destination is strange? For an increasing number of physicists, the second approach seems more honest. Reality has no obligation to match our intuitions. If the math says the universe branches, perhaps it branches. The mathematical foundation of quantum branching lies in a deceptively simple equation written by Erwin Schrödinger in 1926. This equation governs how quantum systems evolve through time. It takes a wave function as input and tells you precisely how that wave function changes from one moment to the next for a single particle. The wave function describes all possible positions and momenta the particle could have. The equation then shows how these possibilities transform as time passes. What makes the Schrödinger equation remarkable is what it doesn't include. There's nothing in the equation about measurement, nothing about collapse, nothing about observers. It simply describes smooth, continuous evolution. The wave function at time t determines the wave function at time t plus 1 second, which determines the wave function at t plus 2 seconds, and so on. The evolution is deterministic. If you know the wave function now, you can calculate it at any future or past time with perfect accuracy. Now consider what happens when you apply this equation to multiple particles. The wave function becomes more complex. Instead of describing one particle's position, it describes all particles' positions simultaneously in a single mathematical structure. This combined wave function captures correlations between particles. When particles interact and become entangled, the equation automatically accounts for this through the structure of the wave function. No special rules are needed. Entanglement emerges naturally from applying the Schrödinger equation to systems of multiple particles. Here's where things become profound. What if you apply the Schrödinger equation to every particle in the universe? You get a single universal wave function that describes the state of all matter and energy everywhere. This wave function evolves deterministically according to the equation. No randomness, no collapse, no special rules for measurement or observation, just one vast mathematical structure, changing smoothly through time according to known physical laws. This universal wave function is the theoretical foundation of the many worlds interpretation. The wave function is not a tool for calculating probabilities. It is reality itself. Everything that exists, has existed, or will exist is encoded in this mathematical structure. When we perceive the universe around us, we perceive one tiny slice of the wave function. We see one branch. The other branches remain just as real, evolving according to the same equation, but forever beyond our direct perception. The structure of this wave function is almost impossible to visualize. It exists in what physicists call configuration space, a realm with 3 dimensions for every particle in the universe. Our observable universe contains roughly 10 to the 80th power particles. The configuration space for our universe, therefore, has 3 times 10 to the 80th dimensions. Human intuition, evolved to navigate 3 spatial dimensions, has no hope of grasping such a space. Even the most abstract mathematical visualizations fall absurdly short. Despite this incomprehensible complexity, the wave function obeys relatively simple rules. The Schrödinger equation is linear, meaning that if you have 2 possible wave functions, their sum is also a valid wave function. This linearity is what allows superposition. An electron can be in state A or state B, so it can also be in a combination of both states simultaneously. The mathematics doesn't prefer one over the other. All possible combinations are equally valid solutions to the equation. This raises a philosophical question that divides physicists. If the wave function contains all possible outcomes superposed together, does anything actually happen? Or is time itself an illusion, with all moments existing simultaneously in the timeless landscape of configuration space? The wave function doesn't change in any absolute sense. It simply is, containing all times, all events, all possible histories as one eternal mathematical object. Some physicists embrace this timeless view. Julian Barber, a theoretical physicist who has worked extensively on the nature of time, argues that the wave function represents a timeless reality. All moments exist simultaneously in configuration space. Our perception of time flowing is an artifact of how our consciousness samples the wave function. past, present, and future are all equally real, spread out across the landscape of quantum possibility. Change is an illusion created by the structure of our memories and the pattern of correlations in the wave function. Others, including Sean Carroll, argue that time remains real even in the many worlds interpretation. Events still occur in sequence within each branch. The branching itself happens in time. As particles interact and entangle, we move forward through the wave function along a particular trajectory, experiencing one moment after another. The wave function evolves. It doesn't simply exist timelessly. Both time and change are fundamental features of reality, not illusions. The debate continues without resolution, but either view leads to staggering implications. If time is real, then the universal wave function describes a universe constantly branching into parallel futures, with each branch containing conscious observers experiencing their own sequence of moments. If time is illusory, then all possible versions of history exist eternally in configuration space, and our sense of moving through time is merely how we perceive our position in this vast mathematical structure. Either way, the universal wave function implies something that challenges our most basic intuitions about existence. Every version of history that could have happened does happen somewhere in the space of quantum outcomes. Your life contains countless variations, all equally real from the perspective of the wave function. Branches, where you made different choices, experienced different events, became a different person. They're not hypothetical possibilities. They're actual realities unfolding in parallel streams of existence. Each one as physical and concrete as the experience you're having right now. The mechanism that divides these branches is quantum decoherence, one of the most important concepts in modern physics. Decoherence explains how the quantum world of superposition and possibility transforms into the classical world of definite outcomes and unique histories. It's the bridge between quantum mechanics and everyday experience, and it makes the many worlds interpretation possible without requiring any mysterious collapse of the wave function. Here's how decoherence works. Imagine a quantum system in superposition, existing in multiple states simultaneously. Perhaps an electron that's both spin up and spin down. As long as this system remains isolated from its environment, the different parts of the superposition can interfere with each other. They maintain quantum coherence. The wave function describing the system shows these interference effects explicitly. Now let the system interact with its environment. Photons bounce off it. Air molecules collide with it. The atoms in a measuring device become correlated with it. Each interaction creates entanglement between the system and the environment. The combined wave function now describes both the system and all the environmental particles it has interacted with as one unified quantum state. From the perspective of someone observing just the system, ignoring all the environmental particles, something remarkable happens. The different parts of the superposition become effectively independent. They stop interfering with each other. The reason is that the environmental particles carry away information about which state the system is in. This information spreads out into the environment so quickly and thoroughly that recovering it becomes practically impossible. The different parts of the superposition are still in the universal wave function, but they're now associated with completely different environmental states. This is decoherence. The superposition hasn't collapsed. All the possibilities still exist in the wave function, but they've become tied to different branches of reality that can no longer interfere with each other. Each branch contains a version of the observer who sees the system in one definite state. From inside each branch, it appears that the system has a unique classical property. The observer can't perceive the other branches because accessing them would require reversing all the entanglement with the environment, an impossibly difficult task. For macroscopic objects, decoherence happens astoundingly fast. A dust particle floating in air undergoes so many collisions with air molecules per second that its quantum superposition decoheres in less than a microsecond. A cat, a person, or any warm object interacts with its environment through countless channels simultaneously: electromagnetic radiation, air molecules, internal thermal fluctuations. The decoherence time becomes effectively instantaneous. This is why we never see cats in superposition of alive and dead. The cat is constantly decohering through environmental interaction. Yet, decoherence doesn't solve the measurement problem in the way the Copenhagen interpretation tried to. Decoherence explains why we don't see superposition at macroscopic scales, but it doesn't explain which outcome we actually observe. After decoherence, the universal wave function still contains all the possibilities. There's a branch where the cat is alive and a branch where it's dead. Both branches are in the wave function. Decoherence just explains why the branches become separate. unable to interfere with each other. This is where the many worlds interpretation becomes essential. Decoherence creates branches. It doesn't select one branch as real and eliminate the others. All the branches exist. You, as an observer, are part of the quantum system. When you become entangled with the cat through decoherence, you split into versions experiencing different outcomes. One version finds a living cat, another finds a dead cat. Both versions are real. Both continue their existence in causally disconnected branches of the universal wave function. Erwin Schrödinger's famous thought experiment with the cat was meant to show how absurd quantum mechanics becomes when applied to large objects. A cat in a sealed box with a quantum-triggered poison device should exist in superposition of alive and dead until someone opens the box. Schrödinger thought this proved quantum mechanics must be incomplete. Cats obviously can't be both alive and dead simultaneously, but quantum mechanics isn't incomplete. The mathematics works perfectly. The issue is not with the physics, but with our intuition about what superposition means. Schrödinger assumed opening the box forces the cat to become either alive or dead, with one outcome becoming real and the other vanishing. The many worlds interpretation says both outcomes are real. When you open the box, you don't collapse the cat's state. You become entangled with the cat. The universe splits. Both versions of you and both versions of the cat exist in separate branches. From your perspective, inside one branch, the cat appears to have been definitely alive or definitely dead the whole time. Your memories make it seem like the outcome was always determined, but that's because your memories themselves branched when you opened the box. The version of you who found a living cat has memories consistent with a living cat. The version who found a dead cat has memories consistent with a dead cat. Neither version can perceive the other branch, because decoherence has made them causally isolated. Schrödinger himself later reconsidered his thought experiment. In 1952, he gave a lecture in Dublin where he proposed something remarkable. He suggested that both outcomes really do happen, they just happen in separate realities that don't interact. He cautioned his audience that this interpretation might sound insane. Then he defended it as the most straightforward reading of the quantum equations. If you follow the mathematics honestly, without adding arbitrary rules about collapse, branching is what you get. The cat experiment reveals something crucial about measurement in quantum mechanics. The cat itself is a measuring device. When the radioactive atom decays or fails to decay, the cat measures this fact by dying or surviving. The cat doesn't need consciousness or intelligence to count as a measurement device. Physical interaction is all that matters. The moment the atom decays, it entangles with the poison mechanism. The moment poison releases, it entangles with the cat. Branching happens at each step. Consciousness enters the picture later, when you open the box. You add yourself to the already entangled system. You don't cause the branching. You join branching that already occurred. The cat was already in superposition of alive and dead states, with both states fully realized in different branches. You simply chose which branch to experience by becoming entangled with the system, or rather, you didn't choose. The quantum interaction determined which branch contains the version of you that has this particular experience. This resolves the measurement problem by showing there never was a problem. The equations of quantum mechanics already describe everything, including observers and measurements. No additional rules are needed, no special status for consciousness, no mysterious collapse. Just quantum mechanics applied consistently to all physical systems, large and small, observed and unobserved, conscious and unconscious. Measurement is simply quantum interaction that creates entanglement and decoherence. But if the many worlds interpretation is correct, we should ask, where do all these parallel universes exist? The answer is subtle. They don't exist elsewhere in three-dimensional space. Our three-dimensional universe doesn't somehow split into multiple copies occupying different locations. Space itself is part of what branches. Each branch contains its own three-dimensional space, its own time, its own matter, and energy. The branches exist in the mathematical structure of the universal wave function, in configuration space. Configuration space is not a physical place you could travel to. It's an abstract mathematical realm that contains all possible configurations of every particle in the universe. Each point in configuration space represents one complete arrangement of all particles. The universal wave function assigns an amplitude to each point. which determines the probability of finding the universe in that configuration if you could somehow measure it from outside. The many-worlds interpretation says all configurations with non-zero amplitude are real. They all exist as different branches of reality. These branches overlap perfectly in three-dimensional space. They occupy the same spatial location we do, but they're causally disconnected. They can't interact under normal circumstances because decoherence has suppressed the quantum interference between them. You can't visit another branch by traveling through space. You can't send messages to other branches using electromagnetic signals. The branches are isolated by the mathematical structure of the wave function, not by distance in ordinary space. Yet some physicists now argue that brief moments of interference between nearby branches might be possible under special conditions. David Deutsch suggests that quantum computers might allow temporary communication between branches. The idea is that during quantum computation, before decoherence fully separates the branches, interference can occur. The computation leverages this interference to solve problems. In a sense, the quantum computer is communicating with versions of itself in parallel branches, sharing computational work across multiple realities. If you're enjoying this journey into the nature of reality, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. If this is true, it would mean the boundaries between worlds are not absolute. Under carefully controlled conditions, with exquisite isolation from environmental decoherence, previously separated branches might merge back together temporarily. This would require reversing the entanglement that split them, an extraordinarily difficult task. Any interaction with the environment destroys the delicate quantum relationships needed for recoherence. But in principle, the mathematics allows it. Some researchers are exploring whether such recoherence could be engineered deliberately. Imagine a quantum system that splits into two branches. In one branch, the system evolves one way. In the other branch, it evolves differently. Then, before decoherence completely isolates them, you manipulate the system to bring the branches back together. The two branches interfere, and information passes between them. You could, in theory, send a signal to a parallel world and receive a response before the worlds separate permanently. This remains far beyond current technology. The theoretical possibility exists in the mathematics of quantum mechanics, but practical implementation faces enormous challenges. The system would need to be isolated from the environment with near-perfect efficiency. Even a single stray photon or air molecule colliding with the system could cause decoherence and ruin the experiment. Current quantum computers struggle to maintain coherence for more than microseconds. Achieving controllable recoherence between macroscopic branches seems impossibly difficult. Yet the mere fact that the equations allow such phenomena suggests something profound. The branches of reality are not infinitely distant from each other. They're parallel streams that have diverged, but, at least in principle, could converge again. Your thoughts might interfere with those of parallel versions of yourself in ways too subtle to notice consciously. The interference happens before decoherence fully separates your brain states. For a brief moment, the quantum superposition of your neural activity includes correlations across branches. Then decoherence washes out the interference, and the branches become isolated. This hints at a deeper unity underlying the apparent multiplicity of worlds. The universal wave function is a single entity, not a collection of disconnected universes. The branches are aspects of this unified whole, like waves on the surface of an ocean. Each wave has its own shape and motion, seemingly independent, but all are manifestations of one body of water. The separation between branches is real, in the sense that they can't interact after decoherence, yet they remain part of one quantum reality. Whether this unity has any practical significance remains unknown. For all purposes related to your lived experience, the other branches might as well not exist. You can't access them, you can't perceive them, you can't verify their existence through direct observation. They affect your reality only through subtle quantum interference effects that wash out almost immediately for macroscopic systems. The branch you experience is, for all practical purposes, the only reality that matters to you. But theoretically, philosophically, the existence of other branches transforms how we understand reality. The universe is vastly larger than the visible cosmos we observe through telescopes. Most of reality is hidden, not by distance or darkness, but by quantum decoherence. Parallel versions of everything exist in superposition, experiencing their own versions of history, evolving according to the same laws, forever separated by the structure of the wave function. Beyond the quantum branching of everyday reality lies an even more staggering possibility. The universe we observe might be just one bubble, in an infinite ocean of bubble universes, each one born from the same inflationary process that created our cosmos, each one potentially having different physical laws and constants. This is the prediction of eternal inflation, a theory that emerges naturally from our best understanding of the Big Bang. In the first tiny fraction of a second after the Big Bang, something extraordinary happened. Space itself expanded exponentially, doubling in size over and over in inconceivably brief intervals. This period, called cosmic inflation, lasted less than a trillionth of a trillionth of a trillionth of a second. Yet, in that time, a region smaller than an atom inflated to larger than the entire observable universe we see today. The expansion happened faster than light, not because anything moved through space faster than light, which relativity forbids, but because space itself was growing. Alan Guth proposed cosmic inflation in 1980 to solve several problems with the standard Big Bang model. Why does the universe appear so smooth and uniform on the largest scales? Why is space geometrically flat rather than curved? Inflation provides elegant answers. By expanding space faster than light, inflation smooths out any irregularities that existed initially and flattens any curvature. Observations of the cosmic microwave background confirm these predictions with remarkable precision. The universe really did undergo exponential expansion in its earliest moments, but inflation has an unexpected consequence that Guth recognized immediately. Once inflation starts in one region of space, it probably never completely stops everywhere. The inflating field that drives expansion is a quantum field. Like all quantum fields, it's subject to fluctuations. These fluctuations create regions where inflation ends and normal expansion begins. Our observable universe exists inside one such region, one bubble where inflation stopped and matter formed. Outside our bubble, space continues inflating. That inflating space spawns more bubbles through quantum fluctuations. Each bubble becomes its own universe with its own Big Bang. Inside each bubble, matter condenses, stars form, galaxies emerge, but the bubbles are separated by eternally inflating space. The space between bubbles expands so rapidly that no signal can ever cross from one bubble to another. Each bubble becomes causally isolated, a completely separate universe. This is eternal inflation. The process never ends globally, even though it ends locally inside individual bubbles. New universes form constantly from quantum fluctuations in the inflating field. They expand and fill with structure. Some might have the same physical laws as ours. Others might have different values for fundamental constants, like the strength of gravity, the charge of electrons, or the mass of quarks. Most bubble universes would have parameters that prevent any interesting structure from forming. No stars, no planets, no chemistry, just empty expanding space or a chaotic mess of energy. A few lucky bubbles, like ours, get combinations of constants that allow complexity to emerge. Matter can clump together under gravity. Nuclear reactions in stellar cores can produce heavy elements. Chemistry can create molecules. Eventually, on rare planets orbiting certain stars, conditions might allow life to arise. But these life-permitting universes are vanishingly rare compared to the vast majority of sterile bubbles. Andre Linde at Stanford University refined this picture of eternal inflation. He demonstrated that eternal inflation is not merely possible, but almost inevitable, given what we know about quantum fields and gravity. Even if inflation stops in most regions, quantum fluctuations will always restart it somewhere. The inflating region grows exponentially, spawning new bubbles which spawn more inflating regions. The process becomes self-sustaining. The multiverse of bubble universes is the natural, perhaps unavoidable, outcome of cosmic inflation. How large is this multiverse? Incomprehensibly vast. Each bubble universe can be infinite in size if the space inside the bubble extends infinitely, and there are likely infinite numbers of bubbles being created constantly throughout eternity. Cosmologists sometimes call this a level 1 multiverse, distinct from the quantum mini-worlds we discussed earlier. But these two types of multiverse might be intimately related. Some theories suggest eternal inflation itself happens differently in different branches of the quantum wave function. The bubbles are separated by space that inflates faster than light. This means they're causally disconnected. Light from one bubble cannot reach another bubble because the space between them expands too rapidly. No particle or signal can cross that barrier. You cannot travel to other bubble universes or communicate with them through any known means. They're isolated not by distance alone, but by the structure of space-time itself. Almost. There is one exception. one circumstance under which bubble universes might touch. If two bubbles form close enough together during inflation, they could collide before the inflating space between them separates them permanently. The collision would send a pulse of energy rippling through both bubbles, like waves spreading from where two raindrops struck a pond. This energy wave would alter the temperature of the cosmic microwave background radiation in both bubbles in a specific pattern. From inside one bubble, looking at the cosmic microwave background, you might see a circular pattern where the collision occurred, a region on the sky where the temperature is systematically different from surrounding areas. Something like a bruise marking where another reality touched ours. Something, perhaps, like the cold spot that astronomers discovered in 2004. NASA's Wilkinson Microwave Anisotropy Probe mapped the oldest light in the universe with unprecedented precision. The cosmic microwave background glows uniformly from every direction, a relic from when the cosmos was just 380,000 years old. Temperature variations across this ancient light reveal how matter was distributed in the early universe. Regions slightly denser than average eventually collapsed to form galaxy clusters. Regions slightly less dense became cosmic voids. The pattern shows how structure emerged from an initially smooth universe. Most of the map looks exactly as our best cosmological models predict. Tiny fluctuations spread across the sky in a pattern matching what inflation produces. But then astronomers noticed something wrong. In the southern sky, a region 5 degrees across, roughly 10 times wider than the full moon, as seen from Earth, registered significantly colder than surrounding areas, not slightly colder. This zone measured 70 microkelvin below average temperature. In some spots, it dropped 140 microkelvin colder. Variations elsewhere in the cosmic microwave background barely exceed 18 microkelvin. Scientists named it the cold spot. Standard cosmology predicts that fluctuations this large might appear across regions 1 degree wide. They should not span 5 degrees. The probability of such a large cold region forming randomly sits around 1 to 2%. Technically possible, statistically unlikely enough to demand explanation. Initial theories focused on a supervoid, perhaps a massive region of space between us and the cosmic microwave background contains far fewer galaxies than average. Light passing through this void would lose energy through a process called the integrated Sachs-Wolf effect, appearing cooler when it reaches our telescopes. In 2015, researchers claimed to find evidence for this enormous void. The structure would stretch 500 million to 1 billion light-years across, one of the largest structures humanity has ever identified if confirmed. But in 2017, a team from Durham University conducted a detailed survey using multiple telescopes and galaxy catalog. They mapped the three-dimensional distribution of galaxies around the cold spot with precision. They compared this data against control regions elsewhere in the sky. The results contradicted the supervoid hypothesis entirely. Galaxy distribution around the cold spot looked normal. No giant void existed there, nothing special about that region of space. To explain why the cosmic microwave background appears colder, the Durham team reached a troubling conclusion. If no supervoid caused the cold spot, then something in the early universe itself must have created a genuinely cold region. But standard models of the Big Bang cannot produce cold patches this enormous. The temperature should smooth out across such large scales through normal processes. Something violated the expected physics. Either the cold spot is a statistical fluke possible but unlikely, or something unusual happened in that direction during the universe's first moments. One explanation stands out as particularly bold. Cosmologist Laura Mersini-Houghton proposed that the cold spot represents a scar from when our universe collided with another universe during the inflationary period. In the first fraction of a second after the Big Bang, while space was expanding exponentially, our bubble might have touched another bubble. The collision sent energy rippling across our universe. This energy wave altered the temperature pattern in the cosmic microwave background in ways we can still detect 13.8 billion years later. The mathematics of bubble collisions make specific predictions. When two universes touch, they release energy at their boundary. This energy propagates outward as a spherical wave. From our perspective, inside one bubble, we would see a circular pattern in the cosmic microwave background. The pattern size depends on when and where the collision occurred relative to our position. The temperature profile should show a particular gradient from center to edge. The cold spot matches these predictions reasonably well, though not perfectly. The European Space Agency's Planck satellite, launched in 2009, provided even more detailed maps of the cosmic microwave background, with resolution 3 times higher than earlier missions. If the cold spot was instrumental error or statistical noise, Planck would expose it. Instead, Planck confirmed the cold spot's existence and sharpened its boundaries. The anomaly is real. Something really did cause that region to be significantly colder than it should be. Researchers analyzed the Planck data, searching for signs of multiple universe collisions. Some theories predict eternal inflation should have caused numerous collisions, not just one. Early analysis suggested possible evidence for 4 separate collision signatures in the cosmic microwave background. Later, more careful analysis found these signals fell within the range of random statistical fluctuations. No definitive proof emerged. The cold spot remains the strongest candidate, sitting at the edge of what standard cosmology can explain through chance alone. Scientists remain divided about interpretation. Some argue we should not invoke exotic physics for a 1% probability event. Unlikely things happen. The cold spot might simply be bad luck, an unusually large fluctuation that occurred by accident. Others counter that 1% is small enough to explore alternatives seriously. Tom Shanks from Durham University stated the stakes clearly. If further analysis rules out all conventional explanations, then the cold spot might represent our first evidence that other universes exist, not as speculation or theory, but as observable fact. What we need are additional ways to test the hypothesis. Future cosmic microwave background experiments will map the sky with even greater precision. If the cold spot is a collision signature, it should have specific fine structure that distinguishes it from random fluctuations. Multiple additional collisions might be found if we examine the data carefully enough, or the improved data might rule out collision explanations entirely, forcing us back to conventional physics or new exotic alternatives. Gravitational wave detectors offer another avenue for testing bubble collision theories. The Laser Interferometer Space Antenna, planned for launch in the 2030 seconds, will measure gravitational waves from the early universe. These waves travel through space essentially unchanged since they were created. Collisions between bubble universes should produce specific gravitational wave signatures that differ from other sources. Detecting these waves would provide direct evidence that our universe touched another reality in the moments after the Big Bang. The implications of such a discovery would be profound. It would confirm that eternal inflation really does produce multiple universes. It would demonstrate that our cosmos is one bubble in an infinite sea of bubbles, most of them forever unreachable, but at least one close enough to leave marks on our reality. The multiverse would transition from theoretical speculation to established cosmology, but there's an even stranger possibility. Some physicists propose that these bubble universes aren't merely separate pockets of space born from inflation. They might be separate quantum branches on a cosmic scale. The quantum mini-worlds interpretation and the inflationary multiverse might be 2 aspects of the same underlying reality. When quantum fluctuations in the inflating field create new bubbles, perhaps they're creating new branches of the universal wave function. Each bubble would be a different outcome of quantum processes in the early universe, all coexisting in superposition. If this is correct, then the entire history of our universe, from the Big Bang to the present, is just one branch of an incomprehensibly larger quantum multiverse. Other branches contain other Big Bangs, other evolutionary histories, other physical laws. The cosmic microwave background we observe is the result of specific quantum events during inflation. In other branches, those quantum events went differently, producing different cosmic microwave background patterns, different distributions of matter, different universes entirely. This unified picture of quantum branching and cosmic inflation remains highly speculative. The mathematics is complex and not fully worked out, but it suggests that the 2 types of multiverse quantum mini-worlds and eternal inflation might ultimately be describing the same phenomenon from different perspectives. Quantum mechanics creates the branches. Inflation gives them space and time to evolve into separate universes. The distinction between quantum branching and bubble formation might be artificial, a limitation of how we currently think about these ideas. Whether the cold spot proves anything remains uncertain. The 1 to 2% probability of random occurrence nags at the debate. Yes, unlikely events happen, but they're unlikely. Should we really accept that we just happen to observe a rare statistical fluctuation? Or does the cold spot's existence hint at something deeper? Some phenomenon our current theories don't fully capture. The uniqueness of the cold spot troubles researchers. If 1% probability events occur randomly, we should see multiple cold spots scattered across the sky. Instead, we see one. This uniqueness is itself unusual. The probability of seeing exactly one anomaly of this size, rather than 0 or several, becomes even smaller than 1% when you account for this. Yet some statisticians argue we're calculating probabilities incorrectly. We scan the entire sky looking for anything unusual. With so many possible anomalies we might have noticed, finding one specific oddity becomes less surprising. The debate will continue until better data arrives. Upcoming surveys will either find additional evidence supporting bubble collisions or constrain the idea so severely that it becomes untenable. Within 2 decades, we should know whether the cold spot is a window into the multiverse or merely a cautionary tale about seeing patterns and randomness. Either way, the fact that we can even ask these questions marks a remarkable moment in science. The existence of parallel universes has moved from philosophy to physics, from speculation to testable hypothesis. The physical constants that govern our universe appear remarkably fine-tuned for complexity in life. Change the strength of gravity by 1 part in 10 to the power of 34, and stars cannot form. Make the electromagnetic force slightly stronger, and atomic nuclei become unstable. Adjust the mass of the electron by a small fraction, and chemistry becomes impossible. The fundamental parameters of nature fall within extremely narrow ranges that permit structure to exist at all. This fine-tuning is not a matter of the constants having mathematically elegant values. They could, as far as we know, have any values whatsoever. The laws of physics don't require specific numbers for these parameters. Yet the values we observe happen to fall precisely in the tiny windows that allow galaxies to form, stars to ignite, heavy elements to be created in supernovae, planets to coalesce, and eventually, life to emerge. The probability seems vanishingly small if the constants were set randomly. Some people see design in this fine-tuning. If the universe appears calibrated for life, perhaps something or someone calibrated it that way. This is the anthropic principle in its strongest form, the suggestion that the universe must have properties compatible with observers because it was intentionally constructed for observers. But most scientists resist this reasoning. Invoking design stops inquiry. It provides no mechanism, no explanation for why the constants have their specific values. It simply restates the mystery as a conclusion. The multiverse offers a different explanation. If countless universes exist with randomly varying physical constants, then some will inevitably have the right combinations purely by chance. We find ourselves in one of those rare universes not because the universe was designed for us, but because we could only exist in universes where conditions permit our kind of life. This is a selection effect, like asking why we live on a planet rather than in the vacuum of space. We observe a life-permitting universe because we cannot exist in the others to observe anything at all. Think of it as a cosmic lottery with infinite tickets. Most tickets are losers, producing universes too hot, too cold, too unstable, or too simple to develop complexity. Stars never form, matter never clumps, chemistry never begins. These universes remain featureless voids or chaotic expanses of energy. But a tiny fraction of tickets win, creating universes where parameters align to allow interesting things to happen. We hold a winning ticket not because winning is common, but because we could never examine a losing ticket. Dead universes have no observers to notice they're dead. In an infinite multiverse, every possible combination of physical constants occurs somewhere. If eternal inflation creates infinite bubble universes, and if different bubbles can have different values for fundamental parameters, then our apparently fine-tuned universe becomes not just probable, but inevitable. Fine-tuning transforms from a mystery demanding explanation into a trivial consequence of living in a vast multiverse. We see what we see because we exist, and we exist because this particular bubble has the right constants. Some physicists dislike multiverse explanations for fine-tuning. They argue it abandons the scientific goal of prediction and explanation. If anything can happen somewhere in the multiverse, what does the theory actually tell us? How do we test it? Others respond that the multiverse is not an assumption added to solve fine-tuning. It's a prediction that emerges naturally from inflation and quantum mechanics. We follow the mathematics where it leads, even to strange conclusions. The multiverse may offend our aesthetic preferences, but reality has no obligation to be elegant. Yet the debate reveals something important about how science works. A theory that predicts everything predicts nothing. If the multiverse contains all possible universes with all possible constants, then we cannot explain why our universe has its specific values. We can only say these values must occur somewhere, and we happen to be in that somewhere. This feels less satisfying than a theory that predicts specific values for fundamental constants based on deeper principles. Perhaps there are such deeper principles waiting to be discovered. Perhaps the constants that seem arbitrary are actually related through some underlying mathematical structure we haven't yet understood. String theory, for instance, attempts to derive all particle properties and forces from the geometry of extra dimensions. If successful, it might explain why constants have their observed values rather than others. But string theory itself appears to have an enormous landscape of possible solutions, each corresponding to different values for observable constants. The multiverse might be unavoidable even in our most fundamental theories. The question of fine-tuning connects to another mystery about our universe, the nature of dark energy. Observations reveal that cosmic expansion is accelerating. Galaxies rush away from each other at increasing speeds. Something is pushing them apart, some form of energy distributed uniformly through space. Physicists call it dark energy, and it constitutes roughly 68% of all energy in the universe. Yet we have no deep understanding of what it is. The simplest explanation suggests space itself has intrinsic energy. Every cubic meter of vacuum contains a tiny but non-zero amount of energy that drives expansion. This is the cosmological constant, a term Einstein introduced in his equations of general relativity and later called his greatest blunder. The problem is that when quantum field theory calculates how much vacuum energy should exist, the answer comes out roughly 10 to the power of 120 times larger than observations allow. This is the worst theoretical prediction in the history of physics. Something is profoundly wrong with our understanding. The multiverse might explain the discrepancy through anthropic selection. If different bubble universes have different vacuum energy densities, most would be unsuitable for structure formation. Universes with very large positive vacuum energy expand so rapidly that matter never clumps into galaxies. Universes with large negative vacuum energy collapse back on themselves too quickly for anything interesting to develop. Only universes with vacuum energy close to zero permit the slow, steady expansion needed for galaxies and stars to form over billions of years. We find ourselves in such a universe because observers cannot exist in the others. The cosmological constant appears fine-tuned not because it was carefully adjusted, but because we inhabit one of the rare bubbles where conditions allow our existence. This anthropic explanation is unsatisfying to many physicists. It abandons the hope of calculating the vacuum energy from first principles. But if the multiverse is real, anthropic reasoning might be the only explanation available for some observed quantities. Some researchers propose something more radical. What if dark energy itself represents leakage from parallel universes? Imagine our universe as a three-dimensional membrane, a brain floating in higher dimensional space. Other brains exist nearby, separated by microscopic distances through extra dimensions we cannot perceive. If gravity can propagate through these extra dimensions, then massive objects in parallel universes might exert gravitational influence on our universe. From our perspective, this would appear as an extra force affecting how galaxies move and how space expands. We would interpret it as dark energy, not realizing we're feeling gravitational pull from matter in parallel realities. This brain cosmology model makes testable predictions. If dark energy comes from nearby brains, its strength should vary slightly over cosmic time or across different regions of space as our brain's position relative to others changes. Standard vacuum energy should be perfectly uniform. Brain leakage would show patterns. No such patterns have been detected yet. Measurements indicate dark energy appears constant within current observational limits, but the data improves continuously as new surveys map the universe with greater precision. The Nancy Grace Roman Space Telescope and the Vera Rubin Observatory, both coming online soon, will measure cosmic expansion history with unprecedented accuracy. If variations appear, we might discover that dark energy has been our first indirect contact with parallel universes all along. String theory, our most promising candidate for a unified theory of physics, requires extra dimensions beyond the 3 spatial dimensions we experience. Early versions needed 9 spatial dimensions plus 1 time dimension for the mathematics to remain consistent. These extra dimensions must be compactified, curled up so tightly that we cannot detect them directly. Every point in our familiar three-dimensional space extends into 6 additional microscopic dimensions, shaped in complex ways. But some versions of string theory suggest extra dimensions might be large rather than small. We live on a three-dimensional surface embedded in higher dimensional space. This brain is our entire observable universe. All matter and radiation are confined to the brain. We cannot move off it or perceive the extra dimensions directly because particles and light are trapped on the brain's surface. Only gravity escapes into the bulk, the higher dimensional space surrounding all brains. Multiple brains might exist floating in this bulk. Each brain is a separate three-dimensional universe with its own matter, energy, and physical laws. The brains might be parallel to each other, like sheets of paper in a stack, or they might be positioned at various angles and separations. The distance between brains through the bulk could be microscopic, even though each brain extends across vast cosmological distances. Neil Turok and Paul Steinhardt developed the ekpyrotic model based on this brain cosmology. They proposed that our Big Bang was actually a collision between two brains. Before collision, both brains existed in cold, empty states. The collision released enormous energy, heating both brains and filling them with radiation. This is what we call the Big Bang. Afterward, the brains bounced apart, moved through the bulk, cooled down, and eventually collided again. The cycle repeats eternally. Each collision creates a new Big Bang. The universe goes through infinite cycles of collision, expansion, cooling, contraction, and collision again. Time has no beginning or end in this model. The ekpyrotic universe is eternal, with our current cosmic epoch merely one cycle among infinitely many past and future cycles. This resolves certain conceptual problems with the standard Big Bang, which requires the universe to begin from nothing at a singular moment of infinite density. The ekpyrotic model makes specific predictions about the cosmic microwave background. Temperature fluctuations should have slightly different statistical properties than standard inflation predicts. Gravitational waves from the Big Bang should have different characteristics. So far, observations have not found clear evidence for or against the model. The differences are subtle and require more precise measurements than current instruments provide. But here's what matters for our discussion of parallel universes. If we live on a brain, then other brains exist nearby in extra dimensions. Those brains are separate universes with their own space, time, and matter. The only connection between them is gravity leaking through the bulk. Brain collisions would leave marks on both universes involved. The collision releases energy primarily where brains touch. From our perspective on one brain, this creates a localized anomaly in the cosmic microwave background. Some researchers argue the cold spot could be evidence of a brain collision rather than a bubble universe collision from inflation. The mathematics differs in details, but the observable consequences are remarkably similar. Both predict circular temperature anomalies in the ancient light from the early universe. Multiple types of parallel universe theory converge on the same prediction that we should see scars in the sky if our reality has touched others. The experimental search for parallel universes is accelerating. Scientists are designing instruments and experiments specifically to test multiverse predictions. Some of these tests could deliver results within the next 2 decades. The Simons Observatory and CMBS-4 project will map the cosmic microwave background with unprecedented precision, potentially revealing fine structure in the cold spot that distinguishes collision signatures from random fluctuations. The Laser Interferometer Space Antenna will detect gravitational waves from the early universe, carrying information about bubble collisions if they occur. Quantum computer development continues at a rapid pace. Current systems have around 1,000 quantum bits, but next-generation devices might reach 10,000 qubits or more. As quantum computers become more sophisticated, they might demonstrate computational capabilities that only make sense if parallel branches exist and contribute processing power. David Deutsch's argument that quantum computers prove the many worlds interpretation could become increasingly difficult to deny as the technology matures. Particle physics experiments at the Large Hadron Collider and future colliders search for signs of extra dimensions. If brains exist in higher dimensional space, high-energy collisions might produce particles that escape into the bulk, appearing as missing energy in detectors. Finding such particles would support brain cosmology and suggest parallel universes exist nearby in dimensions we cannot directly perceive. All these experimental approaches share a common feature. They transform the question of parallel universes from philosophical speculation into testable science. Within our lifetimes, we may know whether other realities exist, not as metaphor or interpretation, but as established fact supported by observational evidence. The cosmic bruise might be explained. The quantum computer might demonstrably harness parallel worlds. The gravitational wave detector might capture echoes of another universe. Or we might discover the multiverse is illusion. Our universe might stand alone. The fine-tuning and quantum weirdness might have prosaic explanations we haven't thought of yet. The cold spot might be nothing more than unlikely chance. Quantum mechanics might permit interpretations that avoid branching. The question remains open, but not unanswerable. The experiments are planned. The instruments are being built. The measurements will be made. Roger Penrose offers a significant challenge to the many worlds interpretation. He argues that the theory fails because it ignores gravity. Quantum mechanics successfully describes particles and fields, but we lack a complete theory of quantum gravity. Penrose claims gravity plays a crucial role in determining what becomes real versus what remains merely possible. His argument centers on the relationship between mass and quantum superposition. Tiny particles like electrons have negligible gravitational fields. They can maintain superposition indefinitely in isolated systems. The wave function describes their state perfectly without requiring collapse. But large objects create significant gravitational fields that curve spacetime around them. If an object exists in superposition of two different positions, it creates two different gravitational fields. Those fields curve spacetime in different ways. Now you have superposition, not just of particle locations, but of spacetime geometries themselves. Penrose argues this situation is physically unstable. The universe cannot maintain contradictory spacetime curvatures indefinitely. He proposes that gravity causes wave function collapse automatically. When an object's superposition creates sufficiently different spacetime geometries, the instability forces one geometry to become real, while others disappear. This happens through gravitational physics, requiring no consciousness, no measurement process, no special rules. Just gravity, doing what gravity does. The threshold for collapse depends on mass and time. An electron can stay in superposition forever because its gravitational field is immeasurably tiny. A dust particle might maintain superposition for 1 second before gravity collapses it. A cat-sized object collapses in microseconds. The more massive the object, the faster gravity forces it into a definite state. Large-scale branching would not occur. The universe splits for quantum particles, but those splits heal rapidly when particles interact with massive objects. Most physicists remain skeptical of Penrose's objective collapse theory. The mathematics is not fully developed. Experimental tests are extremely difficult because predicted effects are subtle. You would need to place increasingly large objects in superposition and measure how long the superposition persists. Current technology can barely create superposition of molecules. Objects massive enough to test gravitational collapse lie far beyond experimental reach. More fundamentally, Penrose's theory requires modifying quantum mechanics, adding new physics beyond the Schrödinger equation. Many physicists prefer interpretations that accept standard quantum mechanics as correct, rather than proposing new collapse mechanisms. The many worlds interpretation requires no changes to underlying physics. It simply takes the equations seriously. Yet Penrose raises a valid point. We don't understand quantum gravity. General relativity and quantum mechanics are incompatible in their current forms. Perhaps their proper unification will reveal that gravity prevents infinite branching, or perhaps gravity itself exists in superposition across different branches. Maybe there's no universal space-time geometry, but rather different geometries in different worlds. The equations of general relativity might describe not one curved space-time, but infinitely many parallel spacetimes evolving independently. Until we have a working theory of quantum gravity, we cannot know which picture is correct. The answer might transform our understanding of both quantum mechanics and parallel universes. The philosophical implications of parallel universes extend far beyond physics. If the many worlds interpretation is correct, questions about personal identity, free will, and the meaning of choice become strange and troubling. Every decision you make creates branches where you chose differently. Versions of you experiencing the consequences of all possible choices exist simultaneously in isolated realities. Does this make your choices meaningful or meaningless? The intuitive worry is that if all outcomes occur regardless of what you choose, then choice becomes empty. You cannot make anything happen or prevent anything from happening. Everything that could happen does happen somewhere in the quantum multiverse. Your agency seems to dissolve. You're not steering your life toward one future rather than others. You're simply determining which branch contains the version of you that has this particular experience. But this misunderstands what choice means in the many worlds framework. When you face a decision and deliberate, you're not determining whether certain branches exist. Quantum branching occurs at a fundamental physical level, driven by particle interactions, not by your conscious choices. Your decisions don't create or destroy branches. What your choices do determine is which branch contains the continuity of your conscious experience going forward. Think of it this way. After a decision point, multiple versions of you exist in different branches. Each version experiences themselves as the unique continuation of your identity. Each has memories of being you, of making their choice, of living with the consequences. From inside each branch, that version's choices are absolutely real and consequential. The version of you in this branch faces the outcomes that flow from your choices here. Other versions made different choices and face different outcomes. Both are real. Both matter to the version experiencing them. This preserves what's important about free will, the subjective experience of deliberation, leading to action, leading to consequences you must live with. You cannot escape responsibility for your choices by appealing to other branches where you chose differently. Those versions bear responsibility for their choices. You bear responsibility for yours. Each branch contains a version experiencing the reality they helped create through their decisions. Some philosophers argue this is sufficient to preserve moral responsibility. Others remain troubled if every possible action occurs somewhere in the multiverse. They ask, what makes any particular action right or wrong? Murder happens in some branches. Heroic sacrifice happens in others. The totality of reality contains all possible moral outcomes. Why should we care about ethics in our particular branch when all branches exist equally? The response is pragmatic. You experience your branch exclusively. You cannot perceive or access the others. For you, your choices are the only ones that matter because they're the only ones whose consequences you will experience. Moral philosophy applies to lived experience, not to the abstract totality of all possible experiences across all branches. You should make good choices because you will experience the results. The fact that other versions made different choices is irrelevant to your experienced reality. There's also a technical consideration involving quantum probability. The Born rule in quantum mechanics says that different branches have different quantum weights or measures. Some outcomes are more likely than others, corresponding to branches with greater amplitude in the wave function. Your choices might influence which branches have higher measure. Making good choices could increase the proportion of high measure branches where positive outcomes occur. This gives moral decisions real stakes, even in a branching universe. The question of personal identity becomes even more complex. Are all the versions of you scattered across branches really you? They share your past up to branching points. They have your memories, personality traits, values, and fears. Yet they diverge over time, becoming different people with different experiences. After decades of branching, some versions might be radically different from others. Which one is the real you? Perhaps the answer is all of them or none of them. The concept of a single, unique self might be an approximation that breaks down when reality branches. What exists is a network of related conscious experiences, each feeling like a continuous self from the inside, each legitimately tracing back to common origins. Personal identity becomes distributed across branches, rather than localized in one unique individual. You are not one person, but a vast family of related persons experiencing parallel lives. This challenges deeply held intuitions about what it means to be someone. We think of ourselves as unified beings with continuous existence from birth to death. The many worlds interpretation suggests this unity is local, confined to individual branches. Across the multiverse, your identity fragments into countless streams. The question, who am I, has no simple answer when you exist in superposition across innumerable parallel realities. Some find this liberating. If multiple versions of you exist making different choices, perhaps you can feel less burdened by regret. Somewhere, a version made the choice you wish you'd made. That version is as real as you are, but others find it disturbing, even nihilistic. If your existence is just one thread among countless others, does your life have meaning? Does anything you do ultimately matter? The answer might be that meaning is precisely what each branch creates for itself. Your life has the meaning you give it through your choices, relationships, and experiences. The existence of other branches doesn't diminish this. Each version of you creates meaning in their own branch. Each life is complete and significant from the perspective of the consciousness experiencing it. The multiverse doesn't erase meaning, it multiplies it across countless parallel lives, each one mattering fully to the person living it. Looking ahead, the next 2 decades will likely determine whether parallel universes are real or merely theoretical speculation. The Euclid Space Telescope, launched in 2023, is currently mapping billions of galaxies. Data arriving throughout the late 2020 seconds and early 2030 seconds will reveal large-scale cosmic structure with unprecedented clarity. If anomalies like the cold spot have patterns we cannot currently resolve, Euclid might detect them. The Vera Rubin Observatory in Chile will photograph the entire visible sky every few nights starting soon. Over a decade, it will create the most detailed map of the changing universe ever made. Anything unusual in the cosmos, gravitational anomalies, unexpected patterns in structure formation, signatures of physics beyond the standard model will appear in Rubin data. If parallel universes leave observable traces, this survey should find them. CMBS-4, the next-generation cosmic microwave background experiment deploying in the late 2020 seconds, will measure ancient light with resolution fine enough to reveal structures invisible to current instruments. The temperature maps will either confirm bubble collision signatures or rule them out definitively. If the cold spot is a scar from touching another universe, CMBS-4 will provide the evidence. If it's random chance, the improved data will show that too. The Laser Interferometer Space Antenna launching in the 2030 seconds will detect gravitational waves from the universe's first moments. These waves carry information about events in the earliest fractions of a second after the Big Bang. Colliding branes or bubble universes should produce distinctive gravitational wave signatures. Finding them would prove our universe has physically touched other realities. Quantum technology advances rapidly. Companies and research institutions worldwide are building more powerful quantum computers. Current systems have around 1,000 qubits. Next-generation devices might reach 10,000 or more. As quantum computers become sophisticated enough, they might demonstrate computational processes that only make sense if parallel branches exist and contribute processing power. The many-worlds interpretation could shift from philosophical stance to technological reality. Particle physics experiments continue searching for extra dimensions. The Large Hadron Collider and planned future colliders might produce particles that escape into higher dimensional bulk space, appearing as missing energy in detectors. Finding such particles would support brane cosmology and indicate parallel universes exist nearby in dimensions we cannot perceive. All these experiments will deliver results within the next 20 years. We are entering an era where parallel universe theories transition from speculation to testable science. The data will either support the multiverse or constrain it severely. Either way, we will know vastly more than we know now. The question that has haunted physics and philosophy for decades, whether other realities exist, might be answered in your lifetime. If the evidence confirms parallel universes, the implications will be staggering. Every physical theory, every understanding of reality, every assumption about existence will need revision. The universe we observe will be recognized as one small part of something incomprehensibly larger. Your life will be understood as one thread in an infinite tapestry of parallel lives. History itself will be revealed as just one branch of countless alternate timelines where events unfolded differently. If the evidence refutes the multiverse, that too will be profound. It would mean our universe stands alone. The quantum strangeness we observe must have some other explanation. The fine-tuning of physical constants must result from deeper principles we haven't discovered. The cold spot must be coincidence. Reality would be smaller than the multiverse theories suggest, but no less mysterious. We would still need to understand why quantum mechanics works the way it does, why the constants have their observed values, why existence takes this particular form. Either outcome advances human understanding. Either way, we learn something fundamental about the nature of reality. The experiments matter not because they confirm or deny what we hope is true, but because they answer questions that can be answered. For the first time, the multiverse hypothesis faces genuine empirical tests. The speculation becomes science. Max Tegmark at MIT proposes the most extreme version of multiverse theory. If a mathematical structure is consistent and well-defined, he argues, it exists as physical reality somewhere. Every possible mathematical universe actually exists. He calls this the mathematical universe hypothesis. This goes far beyond quantum many worlds or eternal inflation. Those theories suggest different branches or bubbles, with varying properties within the same mathematical framework. Tegmark suggests entirely different mathematical structures. Universes where time has 2 dimensions, universes where space has 17 dimensions. Universes governed by mathematical laws we cannot imagine. Why would all mathematical structures exist as realities? Tegmark argues from a principle of democracy. If some mathematical structures correspond to physical universes, why only certain structures? What makes our mathematics special? Unless some external selector chooses which mathematics becomes real, the simplest assumption is that all consistent mathematics generates reality. If one mathematical structure can be physical, all can be. Our universe appears to be purely mathematical in nature. Every physical law can be expressed as equations. Every property of matter and energy corresponds to mathematical structures. Space and time form mathematical geometry. Quantum states live in abstract vector spaces. Perhaps reality doesn't use mathematics to describe itself. Perhaps reality is mathematics. Physical existence might be indistinguishable from mathematical existence. We are patterns within a vast mathematical structure. Consciousness emerges from sufficiently complex mathematical processes. If this is correct, then asking why our universe has its particular structure is like asking why the number 7 has its particular properties. 7 exists necessarily as part of mathematical reality. Our universe exists necessarily as one structure among all possible structures. The mathematical universe hypothesis represents the ultimate multiverse infinite universes, with every conceivable mathematical law. Critics argue this is untestable and therefore unscientific. How could we verify that universes with completely different mathematics exist? We're trapped inside our structure, unable to observe others. Tegmark responds that the hypothesis does make predictions. We should find ourselves in a typical universe among all universes that can support observers. Most mathematical structures probably cannot generate complexity or life. We should expect to inhabit a universe from the subset that allows structure formation. Our universe appears well suited for complexity, with no obvious reason to be that way except anthropic selection from a vast space of possibilities. Whether Tegmark is right remains unknown, but his hypothesis represents the logical endpoint of multiverse thinking, not just many universes with different properties, but infinite universes with every possible mathematical foundation. If this is reality, then what we observe is vanishingly small compared to what exists. Reality is vaster and stranger than even the wildest scientific speculation suggests. Bringing all these threads together, we see multiple independent lines of reasoning converging on the same conclusion. Quantum mechanics, when followed honestly without adding collapse, implies branching realities. Cosmic inflation, when extended through quantum fluctuations, implies eternal creation of bubble universes. String theory and brain cosmology imply parallel universes in extra dimensions. The mathematical structure of physical law might imply universes with all possible mathematical foundations. Fine-tuning of constants makes sense if countless universes exist with varying parameters. Dark energy might be gravitational leakage from nearby realities. These aren't arbitrary speculations. They're conclusions that emerge from taking our best physical theories seriously. The multiverse isn't an assumption we make to solve problems. It's a prediction that keeps arising from different directions. Quantum mechanics predicts it. Cosmology predicts it. String theory predicts it. The mathematical structure of physical law might require it. The convergence is striking. Does this mean parallel universes definitely exist? No. The evidence remains incomplete. The theories are not yet fully developed. Alternative explanations might still be found for quantum mechanics, fine-tuning, and cosmic anomalies. But the weight of theoretical reasoning and the growing body of observational hints suggest we should take the possibility seriously. We may live in a multiverse vastly larger than the visible cosmos, with our observable universe being one thread in an infinite tapestry of realities. If so, then you, the conscious observer experiencing these words, are part of something incomprehensibly vast. You exist in countless forms across parallel branches, each version living their own life, making their own choices, creating their own meaning. The person you are is one manifestation of a distributed identity spanning the multiverse. Your experiences matter fully to you, while being one small part of a much larger whole. Perhaps this is the final lesson of quantum mechanics and cosmology. Reality is not what it appears. The solid, unique, definite world we perceive is a local phenomenon. one branch of a universal wave function, one bubble in an infinite sea of bubbles. The universe is not a single story, but countless stories unfolding simultaneously, each one as real as the others, each one forever separated from the rest by the structure of quantum mechanics and space-time. We stand at a remarkable moment in human history. For the first time, we have the tools and theories to test whether this vision of reality is correct. Within your lifetime, we may know the experiments are launching, the observations are planned. The question of parallel universes will be answered not by philosophy, but by data. We will look at the sky, examine cosmic radiation, study quantum computers, and know whether other worlds exist. Whatever we discover will transform human understanding. If parallel universes are real, we'll recognize our existence as vastly larger than we imagine. If they're not, we'll understand why reality appears quantum, why constants seem fine-tuned, why the universe has the structure we observe. Either way, we advance. Either way, we learn. The mysteries that seem purely philosophical become scientific questions with empirical answers. The many worlds interpretation of quantum mechanics, the eternal inflation of cosmology, the extra dimensions of string theory. These aren't science fiction, they're serious physics emerging from our most successful theories. They may be wrong, but they might be right. And if they're right, then reality is far stranger, far vaster, far more wondrous than everyday experience suggests. You are not alone in experiencing existence. Countless versions of you exist across parallel branches, each one convinced they're the only one, each one creating meaning in their corner of the multiverse. This is where physics has led us. From the double-slit experiment to the cosmic microwave background, from quantum entanglement to cosmic inflation, the evidence keeps pointing toward a universe that branches, that multiplies, that exists in superposition across countless parallel realities. Whether this vision is correct will be determined not by intuition or preference, but by observation and experiment. The answer is coming. Within decades, we will know whether other universes exist or whether we truly are alone in a single, unique reality. Until then, we live with uncertainty and wonder. We make our choices, knowing they might spawn branches. We observe the cosmos, looking for scars where other realities touched ours. We build quantum computers that might harness parallel worlds. We are explorers at the edge of the knowable, asking questions that seemed impossible to answer, finding ways to answer them anyway. And perhaps that is the deepest truth, that reality is bigger than we imagine, stranger than we expect, and more beautiful than we dare hope. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.